Hey guys, it's Mrs. Shevchuk, and today we're going to be learning about negative exponents and how we can apply the properties of zero and negative exponents to simplify expressions. We'll be working in your Module 8 packet starting on page 14. So please make sure you have that ready before you continue with the video. One thing that's really important to know is when we're talking about simplifying expressions, in order for it to be simplified, it has to contain only positive exponents. Each base can only appear one time. There are no powers of powers, so we don't have like an exponent raised to an exponent. And then all of our fractions are in their simplest form. These four things are really important to know so that you can kind of test whether each of your expressions are as simplified as they can be. To get started, I'd like you to try the 5 warm-ups on page 14 of your packet, and then push play when you're ready to check. All right, for our first one, I need to apply the quotient of powers rule, and I say x to the 7 minus 6, that's 1, times y to the 12 minus 3, that's 9, or I can just say x times y to the 9th. When I look at the second one, I notice something right away, that 4 and 6 can be simplified. I'm going to do that before I start working with my exponents, just because it'll make the numbers a little easier to work with. So now I have 2 to the 3rd power times x to the 9th power divided by 3 to the 3rd power y to the 12th power. And then 2 to the 3rd is 8, x to the 9th divided by 27, y to the 12th. If you didn't do this simplifying step first, you would just have some much larger numbers here first that you would then need to simplify, but you'd get to the same answer in the end. Now, number 2 down below, I realize I have some factors on top and bottom I can cancel out. They equal 1 when I divide. So 7 divided by 7 is 1. And then, I see that y and y make 1. And then I'm going to simplify 12 divided by 4. I'm going to divide 4 out of this one, and I'm going to divide 4 out of that one. And then I see x to the 4th on bottom and x to the 5th on top. So I'm going to divide those 4 out, and then that leaves me with just x to the 1st up above. And I notice everything on bottom is now canceled out, and everything on top needs to be simplified. So I have 3 times, we have x times x, so that's x squared, times y squared. And there is my simplified expression. For number 4, I know any number divided by itself is 1, straightforward. And then number 5, I kind of see two things. I see 3 to the 2nd power divided by 3 to the 2nd power. That's 3 to the 2 minus 2, or 3 to the 0. But I also notice anytime I have one number divided by itself, it's going to equal 1. So we're seeing here 3 to the 0 power is the same thing as 1. That expression simplifies to 1. Page 14 reintroduces us to the zero exponent rule. So they give us a quotient of 5 to the 7th divided by 5 to the 7th. And we can show that if we expand this out, right, 5 times itself 7 times, 1, 2, 3, 4, 5. And divide by 5 times 5 times 5 times 5 times 5 times 5. 1, 2, 3, 4, 5. All right, when I expand that out, and then I cancel out any one that equals 1. 5 divided by 5 is 1, 1, 1, 1, 1, 1, and 1. And so what I'm left with is just 1. So that's how we can show it when we're expanding. But if I want to use the quotient rule says, hey, when you are dividing and the bases are the same, you can subtract the exponent. So this is the same as 5 to the 7 minus 7. Well, 5 to the 7 minus 7 is 5 to the 0. Well, we just proved that 5 to the 0 equals 1 by expanding it out, and now we've used the quotient rule to prove the same thing. We could show the same thing with this next expression, x to the 15th over x to the 15th. If I expanded that out, I would divide out all my x's and I would be left with 1. If using the quotient rule, I have x to the 15 minus 15, which is x to the 0, or that's going to be equal to 1. All right, so our algebraic rule here is a to the 0 power is equal to 1. And that's true for any non-zero base. One thing to pay attention to, though, is that only the base with an exponent of 0 is equal to 1, and you'll see what I mean by that in a couple examples. All right, so to sum this up in your packet, we're going to say any non-zero number raised to the 0 power is equal to 1. 30 to the 0 is 1. X over y to the 0 power is 1. 8/3 to the 0 power is 1. Right, so if we take a look at all these different expressions down below, some will be really easy, like letter A, 3 to the 0 power. That's just 1. But watch out for letter E. I'm going to jump over here. If I have 2x to the 0 power, remember the exponent on that 2 is really a 1. Only the x has an exponent of 0. So this would be 2 to the first power times x to the 0 power. So 2 times 1, which is just 2. All right. Letter B here is just going to equal 1. Letter F looks real complicated, but look at it's everything within here to the 0 power. That's also just 1. Let's look at letter C. I have a to the 4th, b to the 0 divided by a squared. So I'm going to rewrite a to the 4th. Okay. Now b to the 0 is equal to 1. And on the bottom, I have a squared. So now I'm going to apply my quotient rule and do a to the 4 minus 2. And I get a squared. If we look at letter D, we want to make sure that we are simplifying this fraction, dividing out any common factors before we go too far on here. So I'm going to take 8 and 56 and divide each of those by 8. All right, and then I'm just going to kind of set up a fraction here and kind of work my way across. So I have 1 times g squared times h. Now j to the 0 is just equal to 1, so I'm going to leave that off. On the bottom, I have 7 times, I have g to the 0, that's 1, and I have h to the 0, that's 1. And I have j to the 11th. I'm going to clean this up just a little bit. I don't need that 1 in front, so I'm going to have g squared h on top and 7j to the 11th on bottom. Finally here, we're going to skip over letter G, but let's take a look at letter H. I've got this whole expression to the 0 power, so that's just 1. And then over here, I have to make sure that I am distributing this 5 squared x to the 4th y squared. And then to simplify that, I have 1 times 5 squared, that's just 25, x to the 4th y squared. All right, page 15 reintroduces us to negative exponents. First things first, if we took a look at this pattern on the table and tried to fill in the rest of the table, could you? Pause the video and take a look and see what you come up with. Push play when you're ready. All right, if we were to follow this pattern here, I'm going to look at this bottom row, and I see that every time I'm doubling this bottom number, right? Times 2, times 2, times 2, times 2. So if I wanted to work backwards to figure out what goes here, I'm going to do the opposite. I'm going to divide by 2. Then I'm going to divide by 2, and I'm going to divide by 2, and divide by 2. So that number is getting half the size of the one that was to the right of it. All right, let's continue that pattern on the table below. We have 3 to the 0, 3 to the first, 3 to the second. So if we work that backwards, I've got 3 to the negative 1, 3 to the negative 2, 3 to the negative 3, 3 to the negative 4. And we've got some more to fill in here. If we have 3 to the first power, that's just 3. 3 squared we know is 9. And so every time I go here, I'm multiplying and getting 3 times bigger than the number to the left of it. Well, so if I need to reverse that, I need to now divide by 3. So 3 divided by 3 is 1. Hey, look at that, 3 to the 0 power is It's 1. We just proved that. Divide this by 3. Now I have 1/3. Divide that by 3. Now I have 1/9. And so on. Divide by 3 and divide by 3. And I end up with 1/81st for 3 to the negative 4th. So I'm hoping as you're doing this, you're sort of seeing this pattern. Look at how these numbers, these denominators, are comparing to these numbers over here. That brings us to a key concept that's not actually written down in your packet. If an expression contains a negative exponent, say like 4 to the negative 3rd, it can be simplified by taking the reciprocal of the base raised to the opposite value of the exponent. And that's true not just for integer bases, but also for fraction bases. Well, let's see what that means. If we have 4 to the negative 3rd, what's the reciprocal of 4? That's 1/4. And then what is the opposite value of the exponent? The opposite value of negative 3 is a positive 3. So 4 to the negative 3rd power is equal to 1/4 to the 3rd. If I have 10 to the negative 5th, that's equal to 1 divided by 10 to the 5th. On the same hand, if I had 1 divided by 8 to the negative 3rd, I still don't want a negative on bottom, so then I have to flip it to the reciprocal, and I do 8 to the positive 3rd. Let's try a few. All right, this table on page 16 is great if you want to kind of see how this rule is developed. You're welcome to go in and expand each of these and then check it using the quotient rule. But I'm going to jump right down to our algebraic rule. And so if we have a to the negative n power, that's equal to 1 divided by a to the n. All right, if we wanted to figure out what 1 divided by 2 to the negative 3rd simplifies to, well, we've got to switch it to its reciprocal and then make the exponent the opposite. So instead of 1/2, I would do 2/1, which is just 2. And my exponent needs to switch to the opposite, which is 2 to the 3rd power. So as an algebraic rule down here, if I have 1 divided by a to the negative n, that's the same as a to the positive n. We will sum this up on the bottom of page 16. So for any non-zero number a and any integer n, a to the negative n is equal to 1 divided by a to the positive n. So 3 to the negative 5th is equal to 1 divided by 3 to the 5th. And 1 divided by m to the negative 2nd power is equal to m to the 2nd power over 1, which is just m to the 2nd power. All right, let's try a couple on page 16. So if I'm starting with this one first, there's a couple ways to do it. I will show you kind of a longer way first. So I have a to the 3rd power. I'm just going to write that out. Times, now I have b to the negative 4th, so we know that's the same as 1 divided by b to the 4th. That made me get rid of my negative exponent. Times, and then I have c to the negative half, or to the negative 2nd power on bottom. So I need to switch that to its reciprocal, c over 1, and make that exponent the opposite. Now when I do that, and I kind of put my a over a 1 there, now I'm going to just kind of multiply straight across and see if we can simplify this a little. So I have a to the 3rd, c to the 2nd, divided by b to the 4th. And I've eliminated all my common bases. I don't have any more negative exponents. That's as simplified as my expression can get. On letter B, I'm going to kind of do something similar. I've got 42 divided by 14. That's going to give me a simplified answer of 3, or that's 3 over 1. All right, now I'm going to kind of go variable by variable. I have r to the negative 2nd divided by r to the 2nd. All right, so I would do, if I use the quotient rule, that's r to the negative 2 minus 2, which means I have r to the negative 4th. I'm not going to leave it like that in the end, but for now I'm just going to keep that. All right, then I'm going to my t. I have t to the negative 6th, and then I have u to the 3 divided by u to the negative 3. And that gives me u to the 3 minus negative 3, which is u to the 6th power. All right, so right now I've got this. I still need to simplify that, though, because I have some negative exponents. I'm going to rewrite that over here. I have 3 times, now I have r to the negative 4th, so that's going to be 1 over r to the 4th times 1 over t to the 6th times u to the 6th over 1. And if I were to simplify this, I have 3u to the 6th over r to the 4th, t to the 6th. Now, I don't know about you, but that felt like a lot of extra work when you may have seen another way that you could do this. So I'm going to leave that there, but I'm going to show this problem again over here, looking at it a little bit differently and kind of talking my way through it differently. Now, I've been doing these a long time, so I kind of start seeing some patterns and shortcuts. When I look at it this way, I say 42 is divisible by 14, and 14 is divisible by 14. All right. Then I'm going to look at my r's next, and I see I have an r to the negative 2nd power. I like to just flip that and put that on the bottom, r to the 2nd on bottom. All right, and then I see t to the negative 6th. That's also on top, but it's a negative exponent, so I'm going to switch it to the bottom. And then I'm also noticing on the bottom I have u to the negative 3rd. And I don't want any negatives, so I'm going to switch that up to the top and do times u to the 3rd. Now, in all that work, what I did was I eliminated all my negative exponents. I did that as a first step. Now I'm just going to go through and simplify what I have left. So on the top of my fraction, I have 3 times u to the 3rd times u to the 3rd, so that's u to the 6th. And then on the bottom of my fraction, I have 1, which I don't really need to use, times r squared times r squared, that's r to the 4th, times t to the 6th. And I got the same answer I did over here, I just got there a little bit differently. So you're going to see different ways to simplify these, and that's okay. Our goal is that we all end up with the same answer in the end. Here's 2 more for you to try by yourself. Pause the video, push play when you're ready to check. All right, here's your answers to check. How did you do? All right, if you got both of those right, wow, you've got a really good understanding of negative exponents already. And if not, don't worry, we're going to continue to practice and you'll have lots of opportunities to get better and better at it. If you have any questions, make sure you reach out to your teacher, and thanks for watching.